Right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. So let's get into this. Okay, there we go. Thing looks set up here. And where'd my pencil go? Over here. Okay. All right, we are good. Let's go. Last time, we finished up some examples of just doing derivatives. Differentiated that guy with the product rule and the chain rule. Differentiated this guy with the quotient rule and the chain rule. Differentiated the ln with first using the log rules and then differentiating it. And did another example just to show you how much easier logs can make things. And we'll probably actually explore a little bit more about that today. If we get that far, when we talk about log differentiation and the benefits of doing that. But for now, we're just going to keep going. We just always have it in our head. We try to apply the simpler rules before the more sophisticated ones. And especially when it comes to logarithms, applying the log rules before you have to apply any calculus rules is usually going to be a nice thing. Then we started talking about implicit differentiation because sometimes we have functions that are implicitly defined, which means they look like this, where your y value, your output variable isn't isolated. It's not explicitly out in the open. It's kind of mixed up with the input variables. And sometimes functions can come to us in that way for whatever reason, but we still want to be able to do calculus with it. We still want to be able to do things like find the derivative and find how fast something is changing and whatever. So we have to talk about something called implicit differentiation, which allows us to find derivatives in the implicit case. The basic intuition behind that, which we looked at last time, was to just essentially differentiate as usual. But whenever you differentiate a dependent variable, you multiply by the prime, right? So if we only have variables x and y, x is my independent variable, y is my dependent variable, then I would just go through and apply all my derivative rules. Power rule is still a thing, chain rule is still a thing, product rule is still a thing, quotient rule is still a thing. All of those are still things. But the only difference is whenever I differentiate a y term, I multiply by y prime, right? And we kind of did that with an example here, where we had this expression with x's and y's kind of mixed up together. 4x squared plus 2xy minus 3x squared y squared plus 4 equals 7 minus ln x. Very long expression. We wanted to find the derivative of y with respect to x. What we did was essentially we just went through and we did all the derivative rules as usual. So the derivative of 4x squared was still 8x, right? But then when I'm doing the product rule on the 2xy, when I differentiated the y part, I had to multiply by y prime. So I differentiated the 2x, left the y, then leave the 2x, differentiate the y, and so on and so forth. You'll notice that when I did the product rule on the second part, the 3x squared y squared, I differentiated the x part, which is 6x, left the y squared, then I left the 3x squared and differentiated the y squared, which is 2y, but then I have to multiply by y prime because it's a dependent variable. The chain rule says there's an inside function here and we need to multiply by its derivative. Once you actually do that, it's all about solving for that guy. And that brings up just another thing that I wanted to mention is that, well, I've mentioned it before, but I guess I can take this opportunity to reemphasize that, is that here is the calculus. And all of this is algebra. It's nothing but algebra, right? Algebra will be the majority of your time in solving any problem. A lot of students who have trouble with calculus, 99.99999% of the time, they don't have trouble with calculus. They actually have trouble with algebra. And they think of calculus as being the hard thing, but really it's not. Pre-calculus and algebra is the hard thing, right? Those are the hard classes. Calculus 1 should actually be pretty easy for you if you're really good at pre-calculus and algebra. And yeah, a lot of students, they fail algebra in pre-calculus class, in calculus class. That's what happens, right? They fail pre-calculus in calculus because they kind of never really took pre-calculus too seriously. And then, you know, they end up in the next level and they're like, I don't understand what's going on. I'm studying all the time. I feel like I understand calculus, but I'm not doing so well. And yeah, you do understand calculus. I'm pretty sure you do, because it's actually not hard to understand. It's just that you don't have the skills to pull off what you need to be able to pull off, and that's what the trouble is. So definitely know your basic rules, know how to factor stuff, how to solve equations, how to sketch stuff, know your log rules, your exponential rules, know how to apply them, know when to apply them. This is all very, very super duper important, and it is what will make or break you. And I've never really seen it the other way around. You know, I've been teaching for over 10 years, teach calculus literally every semester that I've been teaching. I've never actually had a student have trouble at calculus where I was convinced that calculus was their problem. It's always algebra. So just be aware of that. But yeah, we got through the calculus part, we did the algebra, and we solved for the y prime. Ultimately, now we got this answer here, and something is very striking about this answer, which you might find strange, is that the y prime involves y's, right? The expression that we have on the right side here has x's and y's mixed in, which is kind of weird the first time you see it. But then when you realize, well, we kind of started out in a situation where the x's and y's were all mixed in. So is it really that odd that at the end they're all mixed in too? Like, not really. But there are going to be some questions and or concerns about how useful is it going to be to have y's in my answer when I don't even have an isolated y. I don't really know what the y is technically, right? Like I don't have y equals, right? What use is it going to be to have a y in my answer right here? Like how usable is that, right? These concerns I'll talk about pretty soon, but for the most part, I'm hoping that you kind of understand what's going on with implicit differentiation. We're of course going to do some more examples, but that was just a quick recap. So we're going to do more on implicit differentiation, and hopefully we can get to log differentiation as well, which is kind of just a variation. Let me make sure where my examples are. Okay, so now I'm going to go back. I'm going to start out with a simpler example than we did last time. I got through that example we did last time because it was just before the test, and I figured it would be very helpful for the test. But I'm going to pull it back. We're going to still talk about implicit differentiation, but we're actually going to go to a simpler example and kind of work our way back up to the level of difficulty that I showed you last time. So let's actually do that. Examples. And in all these, we're going to find y prime equals dy dx. Okay, so that's the goal. Here is the first problem. If I told you that xy equals 1 and ask you to find y prime, how would you actually go about doing this? Now, there's of course one way to do this. Is to rewrite it explicitly. Right? So I could actually, if x times y equals 1, well, this really means that y is 1 over x, doesn't it? Now, I can actually just divide by x and solve for y. Not a big deal. I know my x is not 0. How do we know x is not 0? How do I know I didn't just divide by 0, did something really illegal? How can I be sure x is, yeah?
Can't have 1 over 0.
Well, I know we can't, but how do I know that I didn't just put myself in that position by dividing by x? How do I know that x wasn't 0 in the first place? Anyone see why I can know that x is not 0 in the first place?
Oh, is it because you multiplied the x by the y, and if it was 0, it wouldn't be 1?
Exactly, right. Because that would not be 1 if x was 0. Right. So I can divide both sides by x, and I don't really have to worry about division by 0 or anything like that, because I know my x is not 0, because if it were 0, then I would not get a 1 there. I would get a 0, right? So this is completely fine for me to rewrite it this way. And once I have that rewritten that way, well, we know what dy dx is, isn't it? It's minus 1 over x squared. We had that before. We knew that like a long time ago, many classes ago. Or we could have done it without solving for y. And this is what we called implicit differentiation last time. So if I have x times y equals 1, what I can do here is I can apply the product rule. Because that's one function and that's another function. They're multiplying each other. And so I can do the product rule. And so I differentiate the first one, leave the second, plus leave the first one, differentiate the second. Then I can go to the other side and differentiate the one. So now here, I differentiated both sides. Now what I can do is I know I want y prime. So that's that guy right here. I just have to solve for it. So what I can do is I can move the guy that doesn't have a y prime to the other side. And then I can take my y prime is going to be minus y divided by x. And so that is the answer. Now, at this point, you might be taken aback just a little bit, and you might wonder, are these the same? I mean, one answer has y's in it, the other one has x's only. How do I know these are the same thing? How do I know that implicit differentiation didn't just mess up and we got like something we weren't supposed to, like there's something wrong with the answer on the right? Because the answer on the left seems very obvious. We totally didn't do anything illegal, right? I could divide by x, that's no problem. X is not 0, didn't do anything illegal, and I know how to differentiate 1 over x. I could know that by heart based on what we did a few classes ago. I could also write that as x to the minus 1 and use the power rule. Either way, negative 1 over x squared is going to be the answer. That's definitely the answer. Right? That's definitely the answer, right? Implicit differentiation is the new kid on the block. How do I know that? How do I know I can trust this kid, right? You know, like I don't know you. I don't know. It's the first time I met this guy. Come on, like he tells me the answer is minus y over x. Why would I believe him? The answer is, of course, is yes, that they are the same. Note that here, we know our y is 1 over x, right? It was easy to actually see that. So therefore, what that kind of means is that when I say my y prime is minus y over x, what I'm really saying, it's minus 1 over x over x. So that actually just becomes minus 1 over x squared. It's actually, it's equal. It's an equivalent way of writing down the answer, right? So it's actually the same. They're both correct. It's just that one of them has y's as a part of the answer, while the other one doesn't. Now, if I knew how to find the y, then I could plug in the expression for y, and I would get the same answer I would have gotten anyway, right? So at this point, you might be thinking, so come on, iPad. So implicit differentiation is optional, right? So you're like, yeah, I mean, it was cool when you were showing me yesterday and I thought I needed this, but now it's like, well, I could have done it without it, right? So why are we doing this again? Okay, hold on. This leads us to the second example. You're going to start to appreciate why we even need this. Let's look at this example. Okay, now here's the question. Could we solve for y here and do things the old way? What do you guys think? Can you guys solve that for y? It's kind of an algebra question, actually. Could you solve that expression for y?
I would say yeah.
Yeah? How would you do that?
Yeah, I'm not sure.
I mean, as far as y goes, what kind of expression are we looking at here?
We know that y is to the second power.
Well, just to release the suspense here, the answer is yes, we can actually solve for y. Look at it this way. Maybe this will help you. If I wrote it that way, would that help? Same thing, I just rearranged the terms. Do you see how we could solve for y now? What kind of expression is that? Right, look at where the y's show up and how they show up. What could you how could you describe this equation if your y's are the focus?
It's a quadratic equation.
It's a quadratic equation. So I have the something times y squared plus something times y plus something with no y's in it equals 0. That's a quadratic equation, right? If I look at this like that's my a, that's my b, and that's my c, what I have here is a y squared plus b y plus c equals 0. It is quadratic. Now, when it comes to quadratics, we have a couple options of how to solve this. We can factor it and set each factor equal to 0, or if it's really messy and we can't really figure out how to factor it, which I wouldn't want to figure out how to factor this, what we would do is the quadratic formula. So by quadratic formula, I know that my y is going to be minus b plus or minus the square root of b squared minus 4ac all over 2a. So in other words, I could solve for y here, and it would be minus b plus or minus the square root of b squared minus 4 times a times, that may now become a plus, times c all over 2 times a. So I could actually solve for y. Now, find y prime the old way. To which I say, nah, not going to do that. Like, no. Like, no, definitely no. I'm just not going to do that. Why aren't you going to do it? I'm not going to do that, Jhevon. Like, that's how you would respond to that question. I gave you that guy and be like, yo, solve for y. Why? Why would I solve for y? And why would I find y prime from this? Quotient rule with like some crazy chain rule. I mean, it doesn't look pretty, right? So I just want you to appreciate that there are times when we can solve for y and do things the old way, but we actually wouldn't want to. So yeah, we could solve for y. And do things the old way. But we wouldn't want to. Okay, so let's go back to our new friend. At this point, you're like, maybe that guy's not so bad. Yeah, I know I only met him like yesterday, but you know, my old friend isn't being too nice right now. So let's go to implicit differentiation. I'm just trying to get in here. I'm gonna let them in. So let's actually go back to this. X squared plus 2xy plus x to the fourth y squared equals 4x cubed. What I would do is I would differentiate both sides. And what this would look like is, well, here I would need the product rule. Because I have two functions. Here I would need the product rule. Because I have two functions. Here, just power rule, right? Power rule plus constant factor rule. Right? So I can immediately just jump into the calculus. I don't have to worry about how am I going to fix this for y, and then after going through a lot of work, end up with something like that to deal with. Like, no, right? So at this point, I'm just going to do the product rule. Differentiate the first term, leave the second. So that's 10x plus 2. Plus, leave the first, differentiate the second. It's just y prime. Plus, differentiate the first term, leave the second. Plus, leave the first term, differentiate the second. Notice that every time I differentiated a y term, I I multiplied by a y prime. This is because of the chain rule. The chain rule says I have to do that. There's some function inside the y. There's some f of x in there that I don't really know what it is. But if I have like an f of x squared, I need to differentiate around it, then multiply by a derivative of the inside. So that's where like the y squared becomes 2y, y prime. Every time you differentiate by differentiate a dependent variable, you have to multiply by the prime. Differentiate the 4x cubed, well, that's 12x squared. So now I'm in a situation where the calculus is done. I've differentiated. Now, because I want the y prime, I just have to solve for it. So the rest of this is algebra. So at this point, we're going to solve for y prime with algebra. So I'm going to isolate the guys with the y primes in them. That is the guy that's the 5x squared plus 2x, as well as the 2x to the fourth y. On the other side, I have 12x squared. I have minus 10x plus 2y minus 4x cubed y squared. Right? So that's the 12x squared is over here. That is over here. That is over here. I want to make sure do a quality check. This is over here. this is over here. That accounts for everybody. So now I would just divide and that's my answer. Now, I mean, if you would like, you can go up here and find the derivative of this guy and see if you'd prefer to do that to this. I think you'll come around to this way. Just a hunch. So that's the derivative. And it does have a y's in the answer, but it is the answer. You can rest assured, even when we have y's in the answer is going to be equivalent. It has to be, because we're using the chain rule. And if you want to know, if you want to have an idea of what the answer would look like had you done it directly, imagine this thing right here in this position, and that position. And imagine the monstrosity that you would have. That's what you would get if you did this directly. And I think just understanding what that would look like kind of tells you it wouldn't be easy getting there, right? To have this whole thing put in these three positions is what your answer would look like if you did it directly. Yeah, not fun. So, but yeah. So at this point, you might be wondering, okay, so implicit differentiation is recommended but not necessary because it makes our life easier. Well, you might have that thought, but allow me to show you another example. It doesn't look as scary as the previous one, but it is scary for a very specific reason. Let's say we have this example and we want to find y prime. Okay, so directly solve for y. All right, so I want to solve for y here. What are we going to do? How do you solve that for y? X squared plus y to the 7th minus 2y equals 3. Are you guys trying to solve for y? Okay, let me save you some time with a hint. Okay, so here's what I would say in regards to solving for y. Impossible. Now, I want you to appreciate that is not hyperbole. When I say impossible, I don't mean it's really hard, or you need some higher level math to figure this out, or, you know, it would take a supercomputer to solve for it. I mean, it's literally impossible. There is a mathematician by the name of Galwa, brilliant mathematician. You don't see the math that he developed at a very young age, early 20s, it's not mathematics that you would see before, like, you're taking a graduate course in mathematics, right? So he developed something called Galwa Theory. His name is pronounced like that because he's French. So it's Galwa. You know, French people in letters, they're like, phonics is a suggestion, right? So it's spelled like Galois, but it's pronounced Galwa. And, you know, very passionate man who was very political activist. You know, he was had very strong opinions, and he was active. He was an activist for his opinions. He did things with his whole heart. He was one of those kind of guys, right? He went into stuff hard, right? He ended up falling in love with this girl who happened to have a boyfriend at the time, and as men were wont to do in those days, you mess with my girl, I challenge you to a duel. Let's fight over her. So he's like, let's do this, bro. So he said like, okay, tomorrow we're gonna do this, right? Then he comes to his senses after his adrenaline goes down. He's like, holy crap, I don't think I'm gonna win. I think I'm gonna die tomorrow. So the night before his death, he started writing out all of these mathematical theories that he had, because he really loved math. He was studying it. He wanted to do something. He wanted to, impact the world, give them his knowledge, all that good stuff. So he's like, I might not be alive tomorrow. So he frantically writes out the stuff that he's been thinking about the night before he dies. And, you know, we have copies of his notebook where he's writing down his math theories. And he's like, I have not time. Just believe me, this is true. I need to move on to this. And he's just scribbling. And, you know, using what he kind of wrote down, we have developed entire mathematical theories to this day that it's not even like trivial theories. It's like, you need to be like taking graduate courses in mathematics before you even see the stuff that he was talking about. So very cool stuff. Of course, he was right. He kind of died the next day. Very tragic story. But he left behind a rich history in the world of math. And among the things that he figured out and wrote down that night was the fact that you see the way that you have a quadratic formula for, you know, you can do the quadratic formula for quadratics and stuff like that. It turns out once you get to the 5th degree or higher, no formula exists. And he kind of proves that you will not be able to find a formula. You might have something that's of a 5th degree power or a 7th degree power or something like that, where you're just lucky and it has a nice answer. But as far as a general formula is concerned, like a quadratic formula, where a quadratic formula can literally solve any quadratic, there's no such thing once you get to degree 5 or higher. This was one of the things that he figured out. And you'll notice here that this has degree 7. It turns out that it's impossible to find a formula for this. It's impossible to find a formula for this. There's no other way to say it. Like, it's not like it's hard. It's literally impossible. You'll never be able to use any of the mathematical expressions that you know, square roots, radicals, divisions, multiplications, exponentiation. No matter what you can do, you will not be able to write down the answer for y in this situation, okay? But what if I want to find the derivative though? What if this is important? And this is actually important. This curve actually has a name. That's how important it is. This curve is called the folium of Descartes. Descartes is another guy. He's big in mathematics. He's also big in philosophy. He's the I think, therefore I am that guy. That's the guy. Also the guy who invented the XY plane, by the way. Literally the XY plane, which seems like it would have existed forever. No, it existed pretty recently. Descartes was the one who did that, which opened up a whole new world of mathematics that allowed us to visualize mathematical equations as curves and functions. So to me, it's one of those things that are kind of on the level of the invention of zero. So Descartes, that guy, is who this curve is named after. And we'd like to be able to find y prime. The curve is not a function, in fact. It looks like this. So it doesn't pass the vertical line test. So this is your x squared plus y to the 7th minus 2y equals 3, not a function. So even if you could solve for y, it wouldn't be a function. It would have to come in multiple pieces. But we have no idea what these pieces would look like because we can't write down a formula for them. And Galwa proved that. So we want to be able to find the slopes of tangent lines to various regions of this curve, which is what we're asking for when we ask to find y prime. So can't solve for y. Implicit differentiation is the only game in town. It's not optional. It's not recommended. If you want a derivative, this is how you do it. So I might show you some example. You're like, yeah, I could just do that the old way though. Or you could be like, yeah, it'll be hard, but I could still solve for y and do it the old way. But no, this is not true. There are times when you literally cannot do it the old way, right? And implicit differentiation is important for that. So now that hopefully I've convinced you that implicit differentiation is actually something that we do need to know, and we should not believe that we could go through life without knowing it if we care about finding derivatives. Let's actually just find the derivative. We're going to go through, differentiate both sides, 2x, 7y to the 6y prime. Every time you differentiate a y, you multiply by y prime. 2y prime equals 0. Now I want to solve for this guy. So that's 7y to the 6 minus 2 equals, bring that 2x over there. And so my y prime is blah. So solving for the function, impossible. Solving for the derivative, easy with implicit differentiation. So that is the derivative. Now, at this point is where the concern I spoke about earlier in class would come up. So yeah, I found the derivative, but it has a y in it though. A y that you told me that we can't even solve for. What use is this, right? So, right, which that is a reasonable concern. It is, yeah. I literally just told you, like, we can never know what the y is, yet I told you the answer with a y in it. Okay, if I can't know what y is, how am I going to know what y to the 6th is? Right? Like, if I could know what y to the 6th is, I could just take the 6th root and know what y is, right? Like, if I can't find y, how am I going to find y to the 6th, right? So now you might notice y is in the answer, and we can't solve for it. Is this useful? And unfortunately, it's not useful, so there's nothing to really, no, I'm kidding. It is useful, yes. Right, here's an example. If x squared plus y to the 7th minus 2y equals 3, find the equation of the tangent line to the curve at the point 2, 1. Now, I want you to check, is 2, 1 on this curve? Right, so if I set x equals 2, y equals 1, and I plug this in, I would get 2 squared plus 1 to the 7th minus 2 times 1 equals 4 plus 1 minus 2 equals 3. Which is supposed to equals 3. So yes, it is on the curve. Now, here's something that might be surprising to you, is that while there are times when we cannot solve for a function y, it's actually relatively simple to be able to find coordinates on that function anyway. So I'd be able to find coordinates. I'd be able to say, if my x is 2, what would the y value be at that point? If my x is 7, what would the y value be? If my x is 13, what would the y value be? And I can literally build up a function out of just like a set of points. And we have techniques to do that. And a lot of it requires computers, right? But it's not impossible. I can actually get this done. Finding points on curves that we know implicitly can be done by methods of, it's called numerical analysis. You guys wouldn't have to take this class, so I wouldn't worry about that. But there's a class called numerical analysis that's about things like this, approximating answers to equations, approximating coordinates on curves, things of that sort. So while I can't give you a formula for y, point by point, I can tell you how y will behave. So I might not know what y is, but I can know a coordinate that's on the function that is described by this curve. Now, how would I go about doing that? Well, I know that the slope is given by y prime evaluated at 2, 1. So this is going to be y prime. What was that? Minus 2x. Seven times y to the 6 minus 2. So this is going to be minus 4 over 5. That is the m. And we know that x1, y1 is equal to 2, 1. So my tangent line is going to be y minus y1 equals m x minus x1. It's going to be plus 8 over 5 plus 1, 5 over 5. So this is going to be y is equal to minus 4 over 5x plus 13 over 5. So that's the tangent line. So on this curve, this impossible curve, if you were to ask me, at the point 2, 1, which I think is going to be somewhere over like here, what is the equation of that tangent line to that curve? Is that a phone going off? Hold on. Okay. So it turns out I can't find the curve, but I can find the derivative, and I can find a tangent line at a convenient point, a point that I care about. Now, remember, this is actually super useful, and we'll actually come back to this topic later on in this class when we cover the topic called linear approximation. The idea is, if I were to zoom in here, remember, if I zoom in far enough, the curve and the tangent line will behave very similarly. So it turns out that locally speaking, I don't know about this function, but if I wanted to guess what it would be doing, how it would be behaving, what I could do is when I'm very close to the point 2, 1, instead of using the formula for the function, I could use the formula for the tangent line because the function is going to behave very similar, right? So we can use y equals minus 4 over 5x plus 13 over 5 as a proxy for the original function y. when close to 2, 1. And you can do this at all points along the function. So if now I'm not interested in that 2, 1, I'm interested at some other point when x is 13, I could figure out what the y coordinate is. I could draw a tangent line. And if I want to know about the function, I would just use the equation of the tangent line to talk about the function. And we're going to do this with linear approximation, using tangent lines to approximate what functions would do. And so we can talk about what functions would do, even when we don't know what the functions are, which is crazy, but calculus allows us to do that. So yeah, that's pretty nice, I think. So you can use implicit differentiation to find derivatives in cases where you don't even know what the function is. And on top of that, you can use this to find tangent lines, which when in the case where you do need to know what the function is, you don't have to know what the function is. You can use the equation of a line in place of the equation of the function once you're close enough. And that's pretty useful. Let me leave a couple more examples for you guys to do, which we'll pick up on tomorrow. And we'll talk about log differentiation tomorrow. So we never got to that today, but it's cool. Try these. Find y prime equals dy dx. Find the derivative of I just have one more here. E to the x plus y squared plus ln of x plus y equals 3. And 2 here, I want you to find dv dp if p plus 5 over v squared times v minus 0.03 equals 9.7, which seems like a weird equation, but it's actually coming from somewhere. So we'll pick up with these and then log differentiation tomorrow. And then maybe even L'Hopital's rule. Maybe we can get to L'Hopital's rule. Let's see. So I already put that in some memes for the class already. So now you'll understand those in hindsight. So as I mentioned in an email, I'll finish grading your test in about a week. So hopefully by Thursday, by Friday, you'll have your grades. And we can move forward with that. That's it for now. So thank you for your time and attention, and hope you have a good rest of your day, and I'll see you guys tomorrow in the next one. Ciao.